Hello children, once again welcome back to Physics with Sanoop. See, in this video we will be discussing electrostatics. So you can expect 3-4 questions at least from this chapter. Okay, now see the first thing, that is the properties of electric charge. See, charge and mass are two macroscopic properties of matter. And first let us discuss the properties of electric charge. See, it is a scalar and it is a derived quantity in SI system, and its SI unit is Coulomb. And next, unlike mass, this charge can be of two types. It can be positive or negative. Okay. Next, see, similar charges repel and dissimilar charges attract. Okay. Next, quantization of electric charge means the charge on any body will be an integral multiple of a basic unit, that is the magnitude of charge on an electron. Okay, so we can write Q equal to plus or minus NE. And see, the next thing is additivity. Okay, see, means the net charge on a body will be the algebraic sum of the charges given to it. Okay, positive or negative. Next, conservation of charge means total charge in a system, isolated system, will be conserved always. Okay, and see these three properties, these three. Okay, means quantization, additivity and conservation. These three properties are called basic properties of electric charge. Okay, next thing, see, charge is always associated with mass, means charge cannot exist without mass. If a body carries a charge, definitely it is a material particle, means it must be having a mass. Okay, next, see, charge is invariant. That is a very important property of charge. See, unlike mass, charge on a body is independent of the speed with which it is moving. See, this m equals m0 divided by root of 1 minus v square by c square. This m0 is the mass of a particle when its velocity is 0, or it is called the rest mass, means the mass of particle when it is at rest. And m is the mass when the particle moves with a speed v. So when a particle moves with a speed comparable to the speed of light in vacuum, then it appears to be heavier. Okay, unlike mass, the charge on a body is invariant, or it is independent of the speed with which it is moving. Okay, next, see, accelerated charge radiates energy. See, in Rutherford's atom model, we have discarded that model because it could not explain the stability of atom. In an atom, according to Rutherford, electrons are revolving in circular orbits around positively charged nucleus. See, when a negatively charged electron revolves around positively charged nucleus, the electrons are being accelerated. Accelerated charge radiates energy according to quantum mechanics. So, Rutherford could not explain the stability of atom. Okay, so accelerated charge radiates energy. Okay, next thing, mass changes when a body is charged. Okay, see, when a body is positively charged, it loses electrons, and when a body gets negatively charged, it gains electrons. So when a body negatively charged, or see, there will be a small increase in its mass because it gains electrons. When a body is positively charged, there will be a small decrease in mass because it loses electrons, and the electrons are very light. Mass is very small compared to the mass of protons. Okay, mass changes when a body is charged. Okay, now see, this is also a beautiful concept. See, this is a charged particle. When its velocity is 0, means it is at rest, then definitely its acceleration is also 0. But the electric field intensity due to that charged particle at rest is not 0. Means a charged particle at rest produces an electric field, but it will not produce any magnetic field. Okay, that is it shows B equal to 0 due to a charged particle at rest. Okay, and this h nu means the energy radiation, that is also 0. Okay, now suppose a particle is moving, means its velocity is not equal to 0. and but it moves with a constant velocity, means acceleration is 0. Then it produces electric field as well as magnetic field, but it will not radiate energy because there is no acceleration. Now here we have a particle carrying a charge. It is moving and also accelerating. So it produces electric field. It is not equal to 0. It produces magnetic field. It is also not equal to 0, but it also radiate energy. Okay. Now see, charge can be detected and measured by a gold leaf electroscope. Using gold leaf electroscope, we can detect the charge. We can identify whether a body is charged or not, and we can also identify the nature of charge on the body. Okay, using the gold leaf electroscope, electrometer, voltameter, ballistic galvanometer, these are used to measure the charge on a body. Okay, next, in a conductor, that is very important. It is very important. In a conductor, charge resides only on its surface, irrespective of its size and shape. Okay, whatever charge is given to a conductor, that will move to the surface and it resides only on the outer surface of the conductor. Okay, that is very important. Next, a body can be charged by three methods, three processes. Okay, friction, then conduction, and then induction. Okay, when two bodies are rubbed together, when two bodies are rubbed together, one body loses electrons and the other body gains. The body loses electrons will acquire a positive charge, and the body gains electrons will acquire a negative charge. Okay, the magnitude of charge on these two bodies will be equal. If this body which loses electrons gains a charge plus Q, then this will get a charge minus Q. Okay, next method. Here the charges on the two bodies are of opposite nature and equal magnitudes. The next method is conduction. This is an uncharged body. This body carries some charge, say positive. When this body is put in contact with an uncharged body, need not be uncharged always. When two bodies are put in contact, charge transfer will take place so as to make their potential equal, or positive charge will move from body at higher potential to the body at lower potential until their potentials become equal. Okay, so in this case, this is the charging body and this is the charged body. Both the bodies have the same nature of charge. If this body carries positive charge, then this body also gets positive charge. Actually, what happens now? A part of the charge carried by this body is transferred to this body. Okay. Now, next method is induction. Here the two bodies, charging body and charged body, are not in physical contact. When this body carrying certain charge is brought near another body, there will be charge separation. Okay, now there will be opposite charge at the nearer end and similar charge at the farther ends. Now when this end is being connected to the earth by a conducting wire, this charge at the farther end will go to the earth. Okay, so here the positive charge goes to the earth. This negative charge will be held by this positive charge. Okay, negative charge, the induced charge is held by this positive charge. Now I have removed, or this is taken away. Okay, and this disconnected from ground. Okay, so this negative charge will get distributed. Okay, now this is Q, that is the charge on the charging body, and this is Q dash, that is the charge acquired by the second body. It was initially uncharged. Then this Q dash equal to Q, negative of Q into 1 minus 1 by K, where K is the dielectric constant of this body. K is the dielectric constant of this body, means the charged body. Okay, now this dielectric constant K is infinite for conductors in electrostatics. The electrical properties of conductors are different when it carries a current and when it does not carry any currents. When it carries no current, we will have to apply the laws of electrostatics. Means the dielectric constant will be 0 for a conductor when there is no current. But if it carries a current, this dielectric constant is not infinite. Okay, now when there is no current through a conductor, see the charge induced in it, Q dash, will be equal to minus Q into 1 minus 1 by K. K is the dielectric constant. It can also be called as relative permittivity or specific inductive capacity. Specific inductive capacity. Okay. This K is the dielectric constant of the charged body. Charged body means, here we have this Q, that is the charge on the charging body, and Q dash is the charge induced on the charged body, and K is the dielectric constant of the charged body. See, when it is a conductor, then Q dash will be equal to minus Q. Means an equal but opposite charge will get induced. Right? Next, let us see the comparison of mass and charge, which are the two macroscopic properties of matter. Okay, first thing, mass is a fundamental quantity in a SI system, whereas the charge is a derived quantity. Okay, now mass can be only one type, means positive only, there is no negative mass. But the charge can be of two types, both positive and negative. Okay, then the important property, see the mass of a particle depends on speed. Okay, by this Einstein's theory of relativity, see mass of a particle moving with a speed v is given by m equals m0 divided by under root 1 minus v square by c square, where v is the speed with which the particle is moving, but the charge of a particle independent of the speed with which it is moving. Okay, so we call charge as invariance. Accelerated mass does not radiate energy, but accelerated charge radiates energy. See, another important comparison is actually both the mass and charge of a particle are quantized. We know that charge is quantized. Charge on any body will be an integral multiple of a basic unit, that is the charge on an electron. See, the mass is also quantized, but the quantum of mass, the mass on any body will be integral multiple of a basic unit, but that basic unit is not yet identified. Okay, and now see, we have Coulomb's law. See, the electrostatic interaction between two charged particles. Okay, we have Q1 and Q2 kept at a separation R. Then the electrostatic force between them is directly proportional to Q1, Q2 and inversely proportional to the square of the distance between them. So we can write F proportional to Q1, Q2 by R square. And this proportionality can be replaced by equal to with a constant of proportionality K. And the value of that constant of proportionality K depends on two factors: the medium in which the charges are kept, and also on the system of units adopted, whether we are using SI unit or CGS unit or any other systems of units. Okay, now in SI system, this K is equal to 1 by 4 pi epsilon, and that epsilon is called the absolute permittivity of the medium in which the charges are kept. Now suppose the charges are kept in vacuum. Okay, then K equals 1 by 4 pi epsilon 0. And its value we can have 9 into 10 raised to 9 Newton meter square Coulomb raised minus 2. And this epsilon 0 is the permittivity of vacuum, and it is equal to 8.854 into 10 raised to minus 12. But we see, all of you must be knowing this 1 by 4 pi epsilon 0 equal to 9 into 10 raised to 9. See, from this value we will get the most useful, beautiful value for the epsilon 0. That is epsilon 0 equal to 1 by 36 pi into 10 raised to 9. Okay, see, you have to use this value. Okay, or this will be this form. When you calculate this, you will get this 8.854. But the value of epsilon 0 in this form will be more useful, because this 36 is a number with so many factors, 2 into 9, 4 into 9, 6 into 6, 3 into 12, like that. There are many factors for 36, so we can easily divide this 36 with so many numbers, or it will be very helpful while doing the calculations. Okay, now next thing that you have to study is the properties. Okay, first thing, see, there are three basic forces in nature: the gravitational force, then electromagnetic force, and nuclear forces. So this electric force is one among the basic forces in nature, so there must be comparison with the other forces like gravitational and nuclear forces. So the first thing, electric force can be attractive or repulsive. Why do we say like that? Because the gravitational force, it is always attractive, but here the force can be attractive or repulsive. You must know it. Okay, and the second thing, inverse square law, it obeys inverse square law, means the force between two particles at rest, electric force, that is inversely proportional to square of the distance between them. Then central force, what do you mean by a central force? It acts along the line joining the centers of the two bodies. Okay, that is what's meant by central force. Now it is a long range force, means it is not a short range force. See, the nuclear force is a short range force. In nucleus, see, in nucleus there are neutrons and also protons. The diameter of the nucleus is, say, 10 raised to minus 15 meter, or this is equal to 10 raised to minus 12 millimeter. Means let us say this will be 1 millimeter divided by 10 raised to 6 into 10 raised to 6. What is 10 raised to 6? It is 1 million. Okay. Now what is 1 millimeter? 1 millimeter is the the least count or the smallest division in a meter scale. Okay, take that 1 millimeter. And that 1 millimeter is to be divided into 1 million equal parts. Take one part out of that 1 million parts. Divide that one part again into another 1 million parts. Then that will be the radius or the diameter of a nucleus. See, in such a small, extremely small volume, there will be strongest attraction between two protons, between a proton and a neutron, and between a neutron and a neutron. Means, see, that is the strongest force in nature, but that will come into play only when the separation is so small. How much small? 1 millimeter is to be divided into 1 million equal parts. Take one part out of that 1 million parts, and this part is to be divided into again another 1 million equal parts. Okay, then one part out of that will be the diameter of the nucleus. When two protons or when two neutrons or a neutron and a proton are at such a small separation, then there exists the strongest force in nature. But that force will act only when these particles are at such a small separation. At normal separation, this force will not act. But electric force is not like that. It will act at any separation. So it's called a long range force. Next, conservative force. See, electrostatic force is conservative in nature, means work done in moving a particle between two given positions against a conservative force will be independent of the path followed. And also, whatever work is done against a conservative force will be stored in the body as its potential energy. So, gravitational force is conservative. Suppose a body, I have lifted a body against gravitational force. Work done is force into displacement. See, the force acting on the body is mg, and equal force is to be applied in the opposite direction in order to lift it. So, the force applied is mg and the displacement is h. Work done will be mg into h, that is mgh. That is the potential energy stored here. When it is released, that potential energy will be converted as kinetic energy. Just like that, suppose we have a positive plate here A negatively charged particle is stuck on that plate. Now suppose I want to remove this negative charged particle from that plate, I will have to apply force and I will have to do work against the electric attraction. So whatever work is done in pulling the particle away from the plate will be stored in the particle as its electric potential energy, and when it is released, that potential energy will be converted as kinetic energy. See, unlike these conservative forces, suppose a body have pushed this body, displaced this body like this. Here the work is done against friction, which is non-conservative or dissipative force. So even if I release that body, it will not come back because work is done against friction. It is a non-conservative force. Whatever work is done against friction will be dissipated in the form of heat and it can never be recovered. So that is what's meant by this conservative force. Okay, now see, it is an action-reaction pair. What? Electric force is an action-reaction pair. Suppose we have got two charged particles, say Q1 and this is Q2. The force exerted by Q1 on Q2 and the reaction exerted by Q2 and Q1 are always equal in magnitude and opposite in direction. Now it is a two-body interaction, means suppose we have three particles A, B and C. Now the force of interaction between A and B is independent of the presence or absence of a third particle C. If there is particle C, there will not be any change in the force between A and B. If there is no any other particle, then also the force between A and B will be the same. So the force of interaction between two given particles is independent of the presence or absence of any other particle. So we can apply the principle of conservation in case of the electric forces. Okay. Now Earnshaw's theorem, it is very important. The equilibrium. What do you mean by equilibrium? See, whenever the resultant force acting on a body is zero, it is said to be in equilibrium. Equilibrium means force is zero. Now, see, in any conservative force field, F is equal to negative of du divided by dr, where u is the potential energy and r is the space variable or say position variable, du by dr. Whenever the force is zero, this is equal to zero. Differential of potential energy is zero. Differential zero means, differential zero means when this u is maximum, its differential is zero. So du by dr 0, force 0, body is in equilibrium, but the potential energy is maximum. If the potential energy is maximum, it must be unstable. Okay, so this is unstable. Okay, unstable. Now see, this du by dr can be zero when this potential energy is minimum also. Okay, then also it is in equilibrium and that equilibrium is stable. Okay. See, another possibility that is this potential energy is constant. Okay, constant. Differential of a constant is also zero. Then the equilibrium is said to be neutral equilibrium. Okay, neutral equilibrium. Suppose we have a bowl and I have kept that bowl on a table upside down. Means see, like this I have kept the bowl, and a small sphere I have carefully placed on the top of the bowl like this. It is in equilibrium. See, it occupies the highest possible position, so its potential energy is maximum. If we displace that body from its equilibrium position, it will never returns to its initial position because the equilibrium is unstable. But suppose we have kept the body in the bowl like this, it occupies the lowest possible position. In this case, potential energy is minimum and equilibrium is stable. If I displace this body and released, it will return to its equilibrium position because it is a stable equilibrium. And suppose I have kept a body over a flat surface like this. Okay, So even if I displace over the flat surface, its potential energy does not change. Everywhere on that surface, its potential energy remains constant. It is in neutral equilibrium. Okay, now Earnshaw's theorem states that the equilibrium of a system of particles under the Coulombian forces alone can never be stable. If there are only electrostatic forces acting on a system, it is unstable, even if it is in equilibrium. Okay, that is the Earnshaw's theorem. Finally, I have to tell you one more thing about the electrostatic force of interaction between two charged particles. See, the electrostatic force is 1 by 4 pi epsilon 0 q1 q2 divided by r square. See, in which that 1 by 4 pi epsilon 0 is positive. 1 by r square is also positive. So the sign of the force of interaction between two charged particles depends on the product q1 q2. See, if the product q1 q2 is greater than 0, means it is positive. So either both the charges are positive or both the charges are negative. Then the force will be positive and it will be repulsive. So positive force means repulsion. If the product q1 q2 less than 0 means it is negative, means one of the charges is positive and the other is negative, or the two charges are dissimilar, then the product q1 q2 is less than 0 or negative, the force will be negative and the force nature of the force will be attractive. So positive force means repulsion, negative force means attraction. Okay. Now suppose we have got 2 point charges q1 and q2. When these two charges are kept in vacuum at a fixed distance say r apart, then the force of interaction between them is F with the suffix 0, that is 1 by 4 pi epsilon 0 q1 q2 by r square. Now the same two charges are shifted to a medium other than vacuum and kept at the same separation. Now the force of interaction between them is capital F equals 1 by 4 pi epsilon, that is the absolute permittivity of the medium, then q1 q2 by r square. So F0 is the force of interaction in vacuum and F is the force of interaction when the same charges are kept at the same separation in any medium other than vacuum. Okay, so F0 by F will be epsilon by epsilon 0. This is the permittivity or absolute permittivity of the medium and this is the permittivity of vacuum. This ratio is called relative permittivity or it is called the dielectric constant. When you call it relative permittivity, it is preferred to represent by epsilon with the suffix r, and when you call it dielectric constant, it is usually represented by capital K. And this same ratio, it can also be called as specific inductive capacity. Okay, and for vacuum, it is exactly 1. Next thing is intensity of electric fields. See, if you want to find the intensity of electric field at any point, you have to place a positive test charge at that point. Suppose you have kept a test charge say Q0, it must be positive by definition. If capital F is the force on that test charge Q0, then Q0 coulombs experiences a force capital F. Then 1 coulomb experiences C F by Q0, and see that Q0, the test charge, must be as small as possible. Okay, in order to get a perfect value for the intensity of electric fields. Now see, the intensity of electric field at any point is the force per unit positive test charge kept at that point. It's the force. So it must be a vector. And see, it is represented by capital E. It is a vector measured in Newton Coulomb raised minus 1. Okay, its unit is Newton Coulomb raised minus 1 and it has one more unit, that is volt meter raised minus 1. Okay, both are SI units, Newton Coulomb raised minus 1 or volt meter raised minus 1. And suppose, see, if capital E is the intensity of electric field at a point, then what does it mean? If we keep 1 coulomb positive charge at that point, that 1 coulomb will experience a force E. So if we keep a charge Q At a point where the intensity of electric field is E, then the force on that charge will be, see, F is equal to, let us say F is equal to Q into E. When a charge Q is kept at a point where the intensity of electric field is E, then the force on it will be QE. Okay, if the charge is positive, the force will be along the direction of the intensity of electric fields, and if the charge is negative, force will be opposite to the direction of the intensity of electric field. And the second thing, see, suppose we want to find the intensity of electric field due to a point charge. We have a point positive charge small q, okay, it is kept in vacuum, and we have to find the intensity of electric field due to this point charge at a distance r from it. We have to keep a test charge Q0, it must be positive, okay, at the point of observation. So the electric force on this test charge will be K, it stands for 1 by 4 pi epsilon 0 Q0 by r square. So on a charge Q0, the force is capital F. So on 1 coulomb the force will be F by Q0, so it is KQ divided by R square. See, in vector form, see, we can write this with the unit vector R cap. Okay, so the intensity of electric field or its magnitude varies inversely with the square of the distance. So if the intensity of electric field is plotted against the distance from the point charge, then this will be the graph. Okay. Now see, the next important thing, that is the electric lines of force. See, electric lines of force are imaginary, not real things, and the concept of electric lines of force is used to represent the electric field. Wherever there is electric field, there will be electric lines of force. If there is a strong field, there will be more lines of force or crowded lines. If there is a weak field, there will be distant lines. If there is no field at all, there will not be any electric lines of force. So electric lines of force are primarily used to represent the intensity of electric field. Okay, and see, its actual definition is they are imaginary lines. It may be straight or curved, such that tangent to the electric line of force at any point will give you the direction of the intensity of electric field at that point. See, that is the only proper definition for electric lines of force. Okay, now see, the properties when we list for electric lines of force, the most important property is that the tangent at any point to an electric line of force will give you the direction of the intensity of electric field at that point. That is the first property. And now the second property, electric lines of force usually originate from a positive charge and terminate in a negative charge, but they can never form closed loops. Okay, now see, yeah, originate from positive and terminate in negative, and the next is they do not intersect at all. That property you must be knowing. Okay, and see, everywhere you might have heard this, they can never intersect. Okay, and the next property that is very important, relative closeness of electric lines of force is a measure of the intensity of electric field. If there are crowded lines, the field is strong. If there are distant lines, the field is weak. Okay, now see, let us take a positive charge and consider the lines of force originating from this charge. Okay, lines of force originating from this charge. See, you may be knowing that as the distance from the point charge increases, the field will become weaker. Okay, or the intensity of electric field goes on decreasing as the distance from the point charge increases. Now see, when we take points near to this positive charge, see, the lines are crowded, or the separation between the adjacent lines are relatively small. Okay, if you take a farther point, see, the relative separation between the adjacent lines has increased. Okay, if you take again, okay, points away from the point charge, the separation between the lines go on increasing. Means if there is a strong field, there will be crowded lines. If there is a weak field, there will be distant lines. So if the field is uniform, or if the intensity of electric field has a constant magnitude everywhere in the space in a given region, then see, if the lines become crowded, the intensity increases. If the lines become distant, then the intensity decreases. So if there is a constant intensity, the lines must be equidistant. See, the direction of the electric lines of force will give you the direction of the field. So if there is a uniform electric field, this electric field being a vector, direction must be constant, magnitude must be constant. So in a uniform electric field, the electric lines of force must be equidistant so as to keep the magnitude constant, and they should be straight in order to keep the direction constant. So in a uniform electric field, electric lines of force will be parallel, equidistant and straight. Okay, parallel, equidistant and straight. See, uniform electric field will be represented by parallel, equidistant and straight lines. Okay, next, do not exist inside a conductor, super property. See, in a conductor, inside the conductor there is no intensity of electric field, so the electric lines of force will not exist inside a conductor because the intensity of electric field inside is zero. And also, see, the electric lines of force are always normal to equipotential surfaces. Equipotential surface means a surface everywhere on it potential will be the same, electric potential will be the same. Surface of a conductor is an equipotential surface. So the electric lines of force can meet the surface of a conductor only normal to it. Now see, suppose we have a spherical conductor here, okay, and the electric line of force, see, this is normal. See, for a spherical surface, the normal at any point is the radius at that point. Okay, so see, this is a radial. So this can be an electric line of force. It does not pass through the conductor. Okay, see, it meets the conductor normal to its surface or radially. Okay, then see, this electric line of force will continue like this. Okay, now suppose we have an electric line of force, say like this. See, this one, it will come and it will meet the surface. See, only radially. See, this lines of force must be normal to the surface of a conductor. Okay, and this line of force, say, it will continue like this. So the electric lines of force in a spherical conductor can meet the surface only normal to it. Okay, that is another important property. Then I have told you earlier, see, the electric lines of force can never form closed loops. And see, the next property is the total number of electric lines of force associated with a charge. Means electric lines of force originating from a positive charge will be Q by epsilon 0. Electric lines of force terminating in a negative charge will be Q by epsilon 0. So these are the important properties of electric lines of force. In addition to that, see, the electric lines of force tends to contract longitudinally and repel laterally. What does it mean? Suppose we have a positive charge, okay, and a negative charge here. Electric lines of force originate from positive charge and terminate in negative charges. See, these electric lines of force have a tendency to reduce their length. See, electric lines of force are from positive to negative. They have a tendency to reduce length. That is what is meant by they tends to contract longitudinally, means lengthwise. What does it mean? See, they have a tendency to reduce their length. Means this positive and negative will move towards each other. Okay, so the attractive property of dissimilar charges are being explained by this. Okay, and at the same time these electric lines of force have a tendency to ripple laterally. What does it mean? Ripple laterally means suppose again we have a positive charge, okay, and another positive charge here. Okay, so the electric lines of force will be like this. So they tends to ripple laterally. Okay, this see along this direction they tends to ripple. Okay, so the electrostatic repulsion is being explained by this property. Okay, electric lines of force will be like this. Okay, so these are the properties of electric lines of force. The main important thing is they do not exist inside a conductor. They meet the surface of a conductor normally. They never intersect, and see, in a uniform electric field they will be parallel, equidistant and straight, and see, crowded lines represent strong field, distant lines represent weak field, and if there is no field, no electric lines of force. Okay, next is electric flux. See, electric flux through a given area is the total number of electric lines of force passing normally through that area. Okay, and what is electric flux density? It is the flux through unit area, and it is equal to the intensity of electric field. See, earlier I have told you, wherever you want to find the intensity of electric field, keep a positive test charge at that point. Find the electric force on it. Then force divided by charge will give you the magnitude of the intensity of electric field. And the electric field intensity direction is along the direction in which a positive charge experiences the force. Okay. Similarly, suppose you want to find the intensity of electric field at this point. Take a small area around that point. That area should be as small as possible. Find the flux through that area. Suppose the flux through that area is delta phi and the area is delta s, then the flux through unit area will be delta phi by delta s. Now see, that area should be as small as possible. How do we say it mathematically? Limit delta s tends to 0. Means it is so small. Then flux through unit area, it's called flux density, and it is equal to the intensity of electric fields. Now area is a scalar, but elementary area means small area can be considered as a vector. If this is area, then this is the outward normal directed outwards, and this is the inward normal directed inwards into the area. See, an elementary area is a vector directed along the outward normal. So if this is an elementary area and this is the outward normal, then area is a vector directed along the outward normal. Now this is the intensity of electric field. What does it mean? See, if the intensity of electric field is capital E, that is the electric flux through unit area. Okay, or this much electric lines of force are passing normally along this direction. Okay, but we want to find the flux through this area. Means we have to find the flux along this normal. See, along this direction the flux density is E. So this E will have a component along this direction, along the normal to the area. That will be E cos theta. Okay, so the electric flux density along this direction is E cos theta. That is the flux through unit area. And we want to find the flux through the area delta S or ds. So through unit area, the flux is E cos theta. Here we have an area ds. So the flux will be E cos theta into ds. Okay, that is, see, E is the magnitude of electric field intensity vector, and ds is the magnitude of elementary area vector. Theta is the angle between them. So E cos theta ds can be written as E dot ds. Intensity of electric field E is a vector. Elementary area ds is also a vector. Two vectors can be multiplied in two different ways. In one way of multiplication, the result obtained will be a scalar, and it's called a scalar product or a dot product. And in the other way of multiplication, the result also will be a vector. It's called vector product or cross product. See, here we have a dot product. Means even though this capital E and ds are vectors, their product will be a scalar. Here the product is the electric flux. So electric flux is a scalar, but the electric flux density is the flux through unit area. It is a vector and it is equal to the intensity of electric fields. So if you want to find the flux through an elementary area ds, then phi, or let us say d phi. Okay, so d phi, this is E dot ds. Okay, electric flux is the dot product of electric flux density or intensity of electric field E and the elementary area vector. Okay, next thing is Gauss's law. See, the total electric flux through any closed surface is equal to 1 by epsilon 0 times the charge enclosed by the surface, and that is the statement of Gauss's law. See, mathematically the total flux through any closed surface is E dot ds closed integral E dot ds. See, E dot ds will give you the flux through an elementary area ds. Actually, the closed surface is divided into a large number of small elements, and this is the flux through each such elements. And see, this is an S. It is an elongated S and stands for summation. Means you have to find the flux through each such small areas, and the sum of the flux through all such elementary areas will give you the total flux, and it is equal to Q by epsilon 0 by ohms by Gauss's law. Okay. Next is this Gauss's law can be used to find the intensity of electric field due to various charge distributions. See, first let us find the intensity of electric field due to a point charge. See, this Gauss's law can be applied for any charge distribution and over any closed surface, but it will be simple when we can have a closed surface that is symmetrical with respect to the charge distribution. Okay, see, let me repeat. This Gauss's law is valid for any charge distribution and for any closed surface, but it will be simple if we can have a surface that is symmetrical with respect to the charge distribution. Here we have a point charge that is the source of the field, and see, we can consider a spherical Gaussian surface with the point charge at its center. So everywhere on this Gaussian surface, the elementary area is directed along the outward normal, or let us say radially outward. The intensity of electric field is also along the same direction. So vectors E and ds are along the same direction. So E dot ds will be E ds. Now every point on this spherical surface are equidistant from the point charge. So the intensity of electric field will have a constant magnitude everywhere on this spherical surface. So this E can be taken outside. Now this is ds, that is the area or the elementary area or area of a small element. The whole spherical area is divided into a large number of such small elements, and see, this is an elongated S and stands for summation. So the sum of the areas of all such elements will give you the spherical area, that is 4 pi r square. By Gauss's law, E dot ds equal to 1 by epsilon 0 times the charge enclosed. The charge enclosed by this Gaussian surface is the point charge, so we will get E into 4 pi r square equal to Q by epsilon 0 and E equal to Q by 4 pi epsilon 0 r square. Now, if this intensity of electric field is plotted against the distance from the point charge, see, this will be the graph. Okay, so we have the electric field intensity due to a point charge as a function. Okay, E equals Q divided by 4 pi epsilon 0 r square, and this is the plot. Now let's try the next case. This is an infinitely long line of charge with the uniform linear charge density lambda. Means charge per unit length is lambda. We have to find the intensity of electric field due to this line of charge at a perpendicular distance r from the line of charge. For For that, we will have to consider a spherical Gaussian surface, okay, of radius small r with this line of charge as the axis. Means line of charge coincides with the axis of this Gaussian surface. Okay, now see suppose the L is the length of this cylindrical Gaussian surface L. Now see, closed integral E dot ds, that is equal to integral E dot ds over the curved surface plus integral E dot ds over the n faces. So if we perform the integration over the curved surface and over two n faces, then we will get the integral over a closed surface. See, over the n faces, see, intensity of electric field is along this direction and the elementary area is along the outward normal. So ds will be along this direction. So E and ds are perpendicular over the n faces. So E dot ds will be 0. Okay, see at the bottom face also. But over the curved surface, see, E and ds are along the same direction. So E dot ds will be equal to E ds. And the integral over the curved surface will be E into 2 pi RL. By Gauss's law, closed integral E dot ds equal to charge enclosed. See, per unit length the charge is lambda. Now our Gaussian surface of length L encloses a line of charge of length L. Per unit length the charge is lambda, so it encloses a length L, means it encloses a charge lambda L. So this is the charge enclosed by epsilon 0. So E into 2 pi RL will be equal to lambda L by epsilon 0 and E will be equal to lambda divided by 2 pi epsilon 0 R. Okay, so when this intensity of electric field is plotted against the distance, perpendicular distance from the line of charge, we will get a curve like this. It is a rectangular hyperbola. It is just like xy equal to constant, or see in thermodynamics we have plotted PV equal to constant. Okay, so the graph, it's called a rectangular hyperbola. Okay, this will be the shape of the graph. Now let's try the next. Here, yeah, we have a spherical shell. Charge, say capital Q, is distributed uniformly over the surface of the shell. Okay, a radius of the shell is capital R. Charge resides only on the outer surface. Okay, so this is the expression for intensity of electric fields. Intensity of electric field is 0 inside the shell, and outside the shell intensity of electric field is kq divided by r square. So this is the expression when small r, distance of the point of observation, means the point where we have to find the field, its distance from the center of the shell. If that distance is greater than or equal to capital R, means on the surface or outside, then we have to use this formula. If that distance is less than capital R, radius of the shell, means the point of observation is inside, then we have to use this formula, or it is 0 electric field inside it. Okay, so if we plot, see here R equal to 0 here, and here R equal to capital R. From the center up to the surface the intensity of electric field is 0, and on the surface it is kq by r square, and if we move beyond the surface it decreases as 1 by r square. Okay, so this is the graph of intensity of electric field due to a spherical shell when plotted against the distance from the center. See, if we consider a conducting solid sphere, whatever charge is given to a conducting solid sphere, the charge will reside only on its surface. So in case of a conducting solid sphere and a spherical shell, charge distribution will be exactly similar. Okay, if the solid sphere is conducting, the charge distribution will be exactly same as that of a spherical shell. So the field will be exactly similar. Okay, now let's try the next case. This is a non-conducting sphere of radius capital R. A charge capital Q is distributed uniformly over the volume of the sphere. Okay, so here the charge, here the sphere is non-conducting. So wherever we put the charge, wherever the charge is given, it will stay there, it will remain there, because it cannot move through the sphere, because the medium is non-conducting. So we can distribute the charge uniformly over the volume of the sphere, and we have such a sphere of radius capital R in which a charge capital Q is distributed uniformly. Okay, so this is the expression or function of the intensity of electric field. Okay, and small r is the distance of the point where we have to find the field from the center of the sphere. Okay, if that distance small r is less than capital R, means our point of observation is inside the sphere. If that small r is greater than capital R, then it is outside. If small r equal to capital R, then it is on the surface. We have to use this formula when small r is less than capital R or inside the sphere, and we have to go for this one when it is on the surface or outside. So when we find the intensity of electric field inside, see, this much is constant. K 1 by 4 pi epsilon 0 is constant. Total charge on the sphere capital Q is constant. Radius of the sphere is not changing. Capital R cube is also constant. So intensity of electric field, that is the, see, we can write like this. Intensity of electric field, this whole thing is a constant into R. If we plot this intensity of electric field along the y-axis, let me replace the quantity plotted along the y-axis as y, and see, this is a constant and this is the quantity plotted along the x-axis. So this is of the form y equal to mx plus c. What stands for c here? See, instead of c, y equal to mx, m means slope. So this is the equation of a straight line passing through the origin. Okay, equation of a straight line passing through the origin. But this equation will be valid only inside the sphere. Means as we move from r equal to, see here r equal to 0 and here r equal to capital R. From r equal to 0 to r equal to capital R, from the center to the surface, the graph, or if we plot intensity of electric field against R, we will get a straight line passing through the origin. Okay, but beyond capital R means outside the sphere. See, this is the expression. So the intensity of electric field varies with 1 by R square. So this curve we have plotted earlier also. So this is the graph. Now let's see the next case, infinite plane sheet of charge with a uniform surface charge density sigma. Okay, this is the surface charge density sigma, small letter sigma. Okay, see, we have an infinite plate like this. See, infinite plate like this. Okay, and the uniform surface charge density means charge per unit area is sigma. Okay, now the Gaussian surface is passing through this plate. Half of the Gaussian cylindrical surface is above and half below. Okay, that is shown here. Okay, now if we take the n phases, see, ds is along the outward normal and intensity of electric field is also along the same direction, and here also intensity of electric field and ds along the same direction. Okay, but over the curved surface, see, when you take the curved surface here, this is the direction of ds, okay, elementary area, and intensity of electric field will be like this. Okay, this is the direction of E. So vector E and vector ds are perpendicular over the curved surface, so E dot ds will be 0. But over the n faces, flat surfaces, E and ds are along the same direction, so E dot ds will be simply the product of E and ds. Okay. Now we have closed integral E dot ds equal to integral E dot ds over the n faces plus integral E dot ds over the curved surface. Over the curved surface, E and ds are perpendicular, so we will get 0. But over the two n faces, it will be EDS plus EDS. Okay, this is Gauss's law, closed integral E dot ds equal to charge enclosed. See, if ds is the area enclosed by this cylindrical Gaussian surface, then the charge enclosed will be sigma ds, because sigma is the charge through unit area and the area enclosed is ds. So the charge enclosed will be sigma ds divided by epsilon 0. This we have calculated and we have got it is 2 EDS. So closed integral E dot ds equal to 2 EDS, and charge enclosed by epsilon 0 is this much. So ds and ds on both sides can be cancelled. So we will get intensity of electric field due to an infinite plane sheet of charge will be sigma over 2 epsilon 0. Okay. Now see, there is no space variable in this. There is no position variable in the expression for the electric field due to an infinite plane sheet of charge. Means if I keep a plane sheet of charge like this, the intensity of electric field at any point in front of it or behind it is independent of the distance of the point of observation from the plane. Means see, the field due to this infinite plane sheet of charge at a distance 1 meter or 2 meter or 3 meter or at any distance, the field will be the same. Okay, and behind also field will be the same. But there is a difference. See, if we suppose this is a positively charged plate. If I keep a positive test charge here, this positive test charge will be repelled by this plate. So it experiences a force like this. Let us take it positive. But if myself keep the same charge here, it will be repelled like this. Means opposites. So the intensity of electric field on the two sides of the plane sheet will be in opposite direction. Suppose I have kept the sheet like this, and let me take the intensity of electric field on right side as towards right, and it is positive. Then the intensity of electric field on left side will be negative. Okay, but it is independent of distance, so we can see this is the field, it does not change with the distance. As the distance increases, the field remains constant. Here also does not change with the distance. Okay. Now see, we have two parallel metal plates carrying surface charge density sigma 1 and sigma 2. Okay. Now suppose this is the region 1. The region in between the two plates, that is represented as region 2, and this is region 3. Okay, we want to find the resultant intensity of electric field at this region. Okay, so if we keep a positive test charge here, that test charge will be repelled by this plate. So the field due to this plate will be towards left. Let me take it negative. Okay, so this is towards left, negative. And the positive test charge kept at this position will be repelled by this plate also, because this also carries a positive charge. So the field due to this plate in this region again towards left, so it also negative. Okay, so the resultant field in this region will be the sum of these two. See, minus 1 by 2 epsilon 0, that is a common factor that can be taken outside. So within bracket sigma 1 plus sigma 2. Now let's consider this region. When a positive touch charge is kept here, it will be repelled by this plate, means along this direction due to the first plate. Let me take it positive because this direction I have taken negative. Now the positive test charge kept at this position will be repelled by this plate, means towards left. So the field in this region due to the first plate will be directed towards right, due to the second plate will be directed towards left. So the field due to the first plate is positive and field due to the second plate is negative. Okay, so sigma 1 by 2 epsilon 0 positive and sigma 2 by 2 epsilon 0 negative. Okay, we want to find the sum of these two. So resultant intensity of electric field in the second region will be 1 by 2 epsilon 0 common, that can be taken outside, and inside the bracket sigma 1 minus sigma 2, sigma 1 minus sigma 2. Okay, now let's find the resultant field intensity in the third region. Again we have to keep a test charge here. It will be repelled by the first plate, means the field due to the first plate in this region will be towards right. Field due to the second plate in this region also will be towards right. Both the fields are positive. Okay, so the resultant field will be the sum of these two. Again we can take 1 by 2 epsilon 0 as common factor. So inside the bracket sigma 1 plus sigma 2. Now as a special case, suppose the two plates are with equal and opposite surface charge densities. Means first plate is positively charged and second plate is with the negative surface charge density of same magnitudes. Okay, now let's see sigma 1, this is equal to plus sigma, and sigma 2, this is equal to minus sigma. Okay, so in the first region, this is plus sigma minus sigma, it will be 0. In the second region, sigma minus minus sigma, it will be 2 sigma. So 2 sigma by 2 epsilon 0, that will be sigma by epsilon 0. So intensity of electric field in the first region 0, intensity of electric field in the second region will be sigma by epsilon 0, and intensity of electric field in the third region, let's find sigma 1 plus sigma 2. Sigma 1 is plus sigma and sigma 2 is minus sigma, so this will be again 0. So when there are two parallel metal plates with equal and opposite surface charge densities, then the intensity of electric field will be there only in between the plates. Okay, and the resultant intensity of electric field in regions outside these plates, means on the left or on the right, will be 0. Okay, field exists only in between the plates. See, next is electric potential. See, electric potential at any point is the work done in bringing 1 coulomb positive charge from infinity up to the point. See, to find the potential, you need not bring 1 coulomb. You can bring any small charge from infinity up to the point. Suppose W is the work done in bringing a test charge Q0 from infinity up to a point. To bring Q0 coulomb, we have to do W work. So in order to bring 1 coulomb, we will have to do W by Q0. Okay, that is the potential at that point. See, by definition, it is the work done per unit positive test charge in bringing from infinity up to the point. So anyway, it is a work done. So it must be a scalar. So electric potential at any point is a scalar. It is measured in joule coulomb raised minus 1, or 1 joule per coulomb is equal to 1 volt. Okay, and it is represented by capital V. Now see, suppose the electric potential at this point, electric potential at this point, suppose the electric potential at this point is capital V. What does it mean? That much work is to be done in bringing 1 coulomb from infinity up to this point. So as to bring 1 coulomb, we will have to do V work. Suppose I have brought Q coulombs and kept at this position. To bring 1 coulomb, we will have to do V work. So to bring Q coulombs, somebody must have done Q into V work on that. That work done will be stored in the system or body as its potential energy. So what is the conclusion? When a charge Q is kept at a point where the potential is V, then its potential energy is Q into V. Okay. Now see, when there are more than one particle, it's called a system. And the potential energy of a system is the work required to assemble the system. Suppose we have a system, let's consider the simplest form of the system. If there is only one particle, we cannot call it as a system. It's only a particle. But whenever there is more than one particle, it can be called as a system. Then the simplest form of the system is a two-particle system. See, we have charges Q1 and Q2. See, we have charges Q1 and Q2 separated by a distance R in vacuum. Okay, so the potential energy of this system is the work required to assemble this system. Means work required to bring this Q1 from infinity up to this point and Q2 here. Okay, so the total work required to assemble the system is given by U equals K Q1 Q2 divided by R, and that is the potential energy of a two-particle system. Okay, because see, we will not have to do any work in bringing Q1, because when we bring Q1, there is no particle anywhere here. So there is no force of attraction or repulsion while we bring Q1. But when we have kept Q1 here and when we try to bring Q2, it will be repelled by Q1 or attracted by Q1. So there will be some force acting on Q2. Okay, so we will have to definitely do some work in bringing Q2. So this is the work required to assemble the system of two particles, and it is the potential energy of the system. Now let's consider a three particle system. Okay, we have Q1, Q2, Q3. Okay, and the separation between any two particles is also represented. So the potential energy of a three particle system is given by 1 by 4 pi epsilon 0. Usually we represent by small k. Okay, then Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q3 Q1 by R31. This potential energy being a scalar, total energy will be simply the algebraic sum of the all potential energies or all work required to assemble the system. Okay, so this is the expression for the potential energy of a three particle system, and this is the expression for potential energy of a two particle system. Now next thing is field and potential. See, when a charge small q is kept at a point where the electric potential is V, then electric potential energy U equal to QV. See, this electric field is a conservative field. Gravitational field is conservative, magnetic field is conservative. Conservative means, see, the work done against such forces will be independent of the path followed. Okay, so in any conservative force fields, force is minus du by dr, where u is the potential energy and r is the space variable, or let us say position variable. Okay, now let me replace this potential energy with qv, where q is the charge and v is the potential. Now this q being a constant, I can take it out, so it will be minus q into dv by dr. dv represents change in potential over a distance dr. Means as we move along or move through a distance dr, the change in potential will be dv. So as we move through 5 centimeters, say the potential changes by 30 volt. Then as we move through 1 centimeter, it will be 30 by 5. Just like that, as we move through a distance dr, the change in potential is dv. So the change in potential per unit distance will be dv by dr, and it is called potential gradient. A similar thing we have studied in heat or transmission of heat. See, as we move through a distance dx, the change in temperature is dt. So the change in temperature per unit distance, it's called dt by dx, and it is the temperature gradient. Okay, here it is the potential gradient. Now dv by dr, see, this F equal to minus q dv by dr, where F is the electric force. Then take this q to the left side, we will get F by q, electric force per unit charge. It is nothing but the intensity of electric fields. So intensity of electric field, we will get this as minus dv by dr. dv by dr is the potential gradient. Minus dv by dr means the negative of the potential gradient, that is equal to the intensity of electric fields. Okay, now what is the significance of that negative sign? See, as we move through a distance dr, potential changes by dv. Potential changes means it can increase with the distance or it can decrease with the distance. That negative sign is to show that as we move along the direction of the intensity of electric field, potential decreases with the distance. See, this is an electric line of force and it is directed towards right. Means the intensity of electric field is directed towards right. As we move through a distance dr, potential will change by dv. Okay, here this negative sign is to show that potential will decrease by dv as we move through a distance dr along the direction of the fields. Okay, so if the potential here it is V, then after a distance dr it will be V minus dv. Okay. Okay, next thing, see, we have intensity of electric field equals minus dv by dr, negative of the potential gradients, and from that we will get dv, potential difference between 2 points, that is equal to minus E dot dr. E, electric field intensity vector, dr, that is also change in the space variable, or or change in position, or let us say the displacement vector, and see the dot product of these two vectors will give you a scalar quantity, that is the potential difference between 2 points. Actually, the potential difference between 2 points is the work done in moving 1 coulomb charge from one point to the other. It is also measured in volt. Okay, so dV equals minus dE dot dr. Okay, now let's see what is next in this chapter. See, we have E equal to minus dV by dr. This E is intensity of electric field and it is a vector, while V, that is the potential at a point and it is a scalar. Okay, then how do we relate this scalar and vector? See, intensity of electric field is this dV by dr, that can be expressed in vector form as minus of, see this you have to read del. See, there is a brand of computer, no, Dell. Just like that, this is del V by del X. Del V by del X, and this is del V by del Y. Okay, del V by del Z. Del V by del X stands for partial differentiation with respect to X. Means, while differentiating with respect to X, you have to keep all other variables as constants. Means, in this case, Y and Z will be constant when we differentiate with respect to X. See, while differentiating, see, when we find del V by del Y, we have to differentiate with respect to Y by keeping Z and X as constants. And this del V by del Z, that is the differential of V with respect to Z by keeping X and Y as constants. Okay, now see, suppose we have a scalar function V equals 6xy square z cube. If you want to find the potential at any point in three-dimensional space, you will have to put the values of x, y and z coordinates in this formula. Means the potential at a general point is given in terms of its x, y and z coordinates. Okay, what is the expression for the intensity of electric field? First, we have to differentiate with respect to x by keeping y and z constants. So 6y square z cube is constant, and the differential of x will be 1. So 6y square z cube into 1. Now let's find del v by del y. We have to differentiate with respect to y. Z and x are constants. So 6x z cube, 6z cube x is constant. Differential of y square is 2y. Okay, next let us find del v by del z. Means differential of v with respect to z. And we have to keep x and y as constants. 6xy square is constant. Differential of z cube will be 3z square. So we have got all the three components and put those C expressions in this equation. We will get the intensity of electric field as a C in component form. Okay. Suppose we want to find the intensity of electric field at the point 1, 1, 1, means x coordinate is 1, y coordinate is 1 and z coordinate is 1. Okay, then see, when we put x and x equal to 1, y equal to 1 and z equal to 1, we will get this E equals minus 6i cap minus 12j cap minus 18k cap. This is how we have to find the intensity of electric field if the potential function is given. Okay. Now see, next is equipotential surface. See, any surface over which electric potential is the same is called an equipotential surface. The surface of a conductor is an equipotential surface, irrespective of its size and shape. Now, what are the properties of equipotential surface? See, first thing, electric lines of force are always normal to equipotential surfaces. Electric lines of force meet equipotential surfaces normally. Okay, and the second, see, the two equipotential surfaces can never intersect. Okay, and the work done in moving a charged particle between any 2 points on a given equipotential surface is 0. Suppose this is an equipotential surface and I have chosen 2 points on the same equipotential surface. Okay, work done in moving a charged particle between these 2 points. W equal to change in potential energy, final potential energy minus initial potential energy. Okay, and that will be equal to change in potential into charge. As this is an equipotential surface, everywhere on that surface potential will be the same. So if A and B are any 2 points on a given surface, potential at B will be equal to potential at A. So the work done will be 0. Okay, so these are the properties of equipotential surfaces. Next, see self-energy. Suppose a spherical shell of radius capital R carries a charge capital Q distributed uniformly over its surface. Then its electric potential energy is given by capital U equals K. K stands for 1 by 4 pi epsilon 0 Q square divided by 2R. Or see, let us say this will be equal to if this K, when we put 1 by 4 pi epsilon 0, it will be Q square divided by 8 pi epsilon 0 R. Okay. Now the self energy of a uniformly charged non-conducting solid sphere means a charge capital Q is distributed uniformly over the volume of a non-conducting sphere of radius capital R. Okay, and the potential energy is 3k Q square divided by 4R. So that will be 3Q square divided by 4 pi epsilon 0 into 5, that will be 20 pi epsilon 0 into capital R. This is the potential energy of a non-conducting solid sphere when it carries a charge capital Q distributed uniformly over its volume. Now let us find the potential due to a charged spherical shell. Here also the charge is distributed over the surface of the sphere. See, it is hollow and the walls are very thin, so it's called spherical shell. Okay, it carries a charge capital Q resides only on its outer surface. Okay, so the potential V equals K capital Q divided by R when the point of observation is inside or on the surface. Means the electric potential at any interior point is the same as the potential on its surface. Okay, at any interior point is the same as the potential on its surface. See here R equal to 0 means at the center of the shell. Okay, potential is K Q by R. As we move from the center to the surface, see the potential remains constant. Okay, so from the center up to the surface, the potential has a constant value and it is equal to the potential at the surface. So it is KQ by R. And as we move beyond the surface or the distance of the point of observation where we want to find the electric potential is greater than the radius of the shell, means the point of observation is outside, then see the potential decreases as 1 by R. Okay, or potential is inversely proportional to the distance. So this will be the graph. It is again a rectangular hyperbola. Okay, now let us see the potential due to a uniformly charged non-conducting solid sphere. Okay, so this is the expression for the potential due to a uniformly charged non-conducting solid sphere. Charge Q is distributed uniformly over the volume of the sphere. Okay, now this is the expression for potential when R is less than capital R, means inside the sphere, and this is the expression for potential when it is greater than or equal to the radius of the sphere, means on the surface or beyond. Okay, it is KQ divided by R. Okay, suppose we want to find the electric potential at the surface. So which formula we have to use? See, this is valid when R greater than or equal to capital R. So if we want to find the potential at the surface where small r equal to capital R, we have to use this formula, this one. Okay, now see, yeah, on the surface when small r equal to capital R, potential is represented by V with the suffix S, potential at the surface. Okay, that is equal to KQ divided by R. And suppose we want to find the potential at the center, then we will have to use this formula because this is valid only when small r less than capital R or inside. Okay, at the center small r equal to 0, the distance of the point of observation from the center. Okay, point of observation is the center itself. So small r equal to 0 and we will get 3kq by 2r, in which kq by r is Vs. So potential at the center V with the suffix C equal to 3 by 2 times V with the suffix S. Okay, so here is the plot. Okay, here r equal to 0 or the potential at the center, that is equal to 3kq by 2r, and see here small r equal to capital R, that is on the surface. On the surface, that is equal to kq by r. Okay, now see potential see potential at the center, potential at the center V with the suffix C. This is equal to 3 by 2 times the potential at the surface. 3 by 2 times 1.5 of the potential at the center. Potential at the surface. Potential at the center is 1.5 times of the potential at the surface. Means potential at the surface plus half of it. See, this is the potential. This is the potential at the surface. Okay, and potential at the center will be this plus half of it. Okay, this plus half of it means it will come here. Okay, now let us see. This is the potential at the center and this is the potential at the surface. Okay, next is electric dipole. See, electric dipole means see two equal and opposite charges separated by a small distance. Okay, that system is called an electric dipole. Okay, see the magnitude of both the charges will be equal and their nature will be different. Means one positive and the other will be negative. See the product of either charge and the separation between them is the magnitude of a vector called dipole moment. And see the direction of the dipole moment is from the negative charge to the positive charge along the axis of the dipole. Okay, so dipole moment we have a vector P and its magnitude is equal to the magnitude of either charge and the separation between them. Separation I have represented by 2a. Okay, so this is a vector directed from the negative to the positive along the axis. Okay, that system is called electric dipole. Now let us find the intensity of electric field due to an electric dipole. See, here is the dipole, negative charge and positive charge. Okay, suppose this negative charge is minus q and positive charge is plus q. Okay, see this is a point along its axis. Okay, so this position is called axial position, or it can also be called as end-on position. See, end-on position or tan A position. Tan A position. Similarly, this is the axis and this is the perpendicular bisector of the axis. If the point of observation is on the perpendicular bisector, then this position can be called as equatorial position or perpendicular bisector or broad-on position, or we can call it as tan B position. Okay, now see the intensity of electric field at any point along its axis is given by, see here I have intensity of electric field along the axis, that is equal to, see on the left side we have a vector and on the right side also we should have a vector, and the direction of both the vectors on left and right side of this equation must be the same. See on the right side I have a vector that is P dipole moment. Okay, all other factors are scalars. So 2k, k is 1 by 4 pi epsilon 0, r is the distance, and in the denominator I have r square minus a square. See, usually the dipole will be very small. Okay, we call it short dipole, means it is its length is extremely small, will be of the order of a micrometer. Okay, so usually this a square will be very small compared to r square, so it can be neglected. And for short dipoles, usually all dipoles will be very short. So for a dipole we can say intensity of electric field along the axis is 2. K stands for 1 by 4 pi epsilon 0 P by r cube, where r is the distance of the point of observation from the center of the dipole. Okay, and what is the direction of this field along the axis? It is along the direction of the dipole moment. See, here I have negative charge here and positive charge here. So the dipole moment is directed from negative to positive. So the dipole moment is towards right. So the intensity of electric field at this position will be along the direction of the dipole moment. See, this is also a point on the axis. So the intensity of electric field at this position also must be along the direction of the dipole moment, that is from left to right. Okay, now let's consider see a point on the equatorial line or perpendicular bisector. Here we have a point. See, this is equatorial position, this is also equatorial position. See the intensity of electric field. See, anywhere on the equatorial line must be along the same direction. Okay. Now, see, this is the expression for the intensity of electric field at the equatorial position. This is minus Kp divided by r square plus a square whole raised to 3 by 2. See, on the left side we have a vector. On the right side also we have a vector. Okay, but there is a negative sign. Means the vectors on the left and right side of this equal to sign are in opposite direction. Means the intensity of electric field at anywhere on the equatorial line is opposite to the dipole moment. Dipole moment is from negative to positive, means from this charge to this charge. So this is the direction of dipole moment. So on the equatorial line, intensity of electric field must be opposite. So at this position, electric field intensity must be, see, right to left. This is also a position on the equatorial line. Here also intensity of electric field must be like this. Okay, here also for a short dipole, A will be much smaller than R. So A square can be neglected compared to R square. So it will be minus Kp by R cube. Please note that the intensity of electric field along the axis is 2 Kp by R cube for a short dipole, but on the perpendicular bisector it is only of magnitude half of the magnitude of the intensity of electric field along the axis, means it is Kp by R cube. Okay, now see what's next here. Yeah, this is the potential due to an electric dipole. See, any point on the equatorial line will be equidistant from negative and positive charge. So both the negative charge and positive charge will produce positive and negative potentials of equal value everywhere on this equatorial line. So the net or total potential at any point on this equatorial line due to this dipole will be 0. Okay, and see, consider a point along the axis. See, at any point along the axis at a distance r, see the potential is given by Kp divided by r square minus a square. Here also for a short dipole this a square can be neglected, so it will be Kp by r square. Okay, now see, this is a general point, not on the equatorial line, not along the axis. Okay, suppose here is the point of observation and the position vector of that point of observation with respect to the center of the dipole. What does it mean? From the center of the dipole we have to draw a line to the point of observation. Then this line, see, this line will be the position vector of the point of observation, means the point where we have to find the field or potential. Okay, so this is the position vector of the point of observation with respect to the center of the dipole or the dipole center when it is chosen as the origin. Okay, if this position vector is inclined at an angle theta with the dipole moment vector, then the potential, and that point is at a distance r from the center of the dipole, then this is the expression for the potential at the point. It is Kp cos theta divided by r square. Okay, what would be the electric potential along the axis? See, if this point of observation is here, okay, so theta will be 0, cos 0 is 1, and it will be Kp by r square, what we have got earlier, see, Kp by r square. Okay, now see what would be the potential on the perpendicular bisector, means the point will be here, where theta equal to 90 degree and cos 90 will be equal to 0. Okay, that we have got. See, potential on the equatorial line equal to 0. Now let's find the expression for the electric field intensity. Okay, at this position, see E equals Kp by r cube 1 plus 3 cos square theta, and the direction is given by tan phi, that is equal to half tan theta, where phi is the angle made by the resultant intensity of electric field. This is the resultant intensity of electric field with the position vector, that is phi. Okay, and see that tan phi equal to half tan theta, right? And E equals Kp by r cube 1 plus 3 cos square theta. Suppose we want to find the field intensity at a point on the axis, means see this point comes here, theta will be 0. Okay, cos 0 will be 1. 3 into cos 0 means 3 into 1, that is 3. 3 plus 1 will be 4 under root, that is equal to 2, means 2 Kp by r cube. That is the result that we have got earlier. Okay, now suppose we want to find the intensity of electric field on the perpendicular bisector. Means the point of observation is here and theta will be 90. Cos 90 will be 0. Okay, so under root there will be only 1. So the field intensity will be Kp by r cube. See, everything same as we got before. Now next thing is, see I have kept a dipole in a uniform electric field. Uniform electric field means intensity of electric field is constant in space. See the value of the intensity of electric field both in magnitude and direction, it is same everywhere in this region. Okay, in such a uniform electric field, suppose I have kept an electric dipole. Okay, such that the dipole moment vector, see from the negative to the positive. Okay, see dipole moment vector from the negative to the positive makes an angle theta with the direction of the field. This is the direction of the field. Okay, angle is theta, right? Then see in a uniform electric field, a dipole experiences no resultant force. Resultant force on it will be 0. But it experiences a torque, a turning effect that will, please listen, that will tend to turn the dipole to get aligned along the direction of the field. See, torque tends to turn the dipole to get aligned along the direction of the field. Means ultimately dipole will be along the direction of the field, or dipole moment and electric field along the same direction ultimately, if the dipole rotates under the action of this torque. Due to this torque, if the dipole rotates, ultimately dipole moment and electric field along the same direction. Okay, now see that torque tau is given by P cross E, and the potential energy of the dipole kept in a uniform electric field will be U equal to minus P dot E. Here we have the cross product because the torque is a vector. Here we have the dot product. Even though dipole moment and the intensity of electric field are vectors, the dot product of these two with a negative sign will give you the potential energy, that is a scalar. Okay, now see, this is the work done in turning the dipole from a position where it makes an angle theta 1 to a position when it makes an angle theta 2 with the direction of the field. This is the work done. Okay, now see initially or in equilibrium, suppose this is the direction of the intensity of electric fields, and suppose I have kept a dielectric dipole here, so the dipole will lie like this. Okay, dipole will be along the direction of the field. Along the direction of the field, this will be the situation. If the dipole is along the direction of the electric field, and if it is not disturbed, it will be there forever because it is in stable equilibrium. Now what happens if I have carefully tilted from this position? Okay, gently tilted from this position through a small angle. Means what I am doing now, see this is the dipole is like this. Now I have tilted the dipole through a small angle and then released. This is tilted through a small angle and then released. what happens? See, the dipole when tilted like this, it will be moving like this. See, it will be moving like this. It will be moving like this. Means, see, it will execute angular SHM. Linear SHM we have studied. SHM stands for simple harmonic motion, special type of oscillatory motion. Linear SHM we have studied, but here it will be angular SHM. Instead of linear displacement, here there will be angular displacement. Instead of linear acceleration, here there will be angular acceleration. Corresponding to restoring force in linear SHM, here there will be restoring torque. See, here is the expression tau equal to P cross E. That is the restoring torque. As it opposes or against the angular displacement, let us represent tau equal to minus Pe sin theta. What is the significance of that negative sign? See, the torque is so as to reduce theta. Okay, that is being shown by this negative sign. See, I have told you, this dipole I have tilted through a small angle. When theta is very small, I can simply replace this sin theta by theta. Okay, so I'll get torque tau equal to minus P theta. And see, when this torque is divided by the moment of inertia, moment of inertia is analogous to mass in linear mechanics. Okay, and torque is analogous to force in linear mechanics. So torque divided by moment of inertia will give you the angular acceleration. See, in linear SHM, linear acceleration is minus omega square linear displacement. The corresponding relation in angular SHM, that is angular acceleration, is minus omega square theta. So children, what stands for omega square in this expression? That is Pe by I. So omega, angular velocity, will be under root Pe by I. Okay, so the time period, that is 2 pi over omega. So 2 pi times under root I divided by Pe. See, this is the period of angular SHM by an electric dipole placed in a uniform electric field. Okay, now suppose the dipole is kept in a non-uniform electric field. Means the intensity of electric field is different at different positions in that region, in that area. Means, see, the intensity of electric field where this negative charge lies is different from the intensity of electric field where the positive charge lies. Okay, in such a situation, the electric dipole will experience an unbalanced force and also a torque. So in uniform electric field, dipole experiences only a torque and no resultant force. But in a non-uniform electric field, it experiences a resultant force as well as a resultant torque. Now let's see the motion of a charged particle through a uniform electric field. Okay. See, when a charged particle is accelerated through a potential difference capital V, potential difference and voltage are exactly the same. See, when a charged particle is accelerated through a voltage V, it acquires a kinetic energy QV. Okay, when Q is accelerated through a voltage V, the kinetic energy acquired by it means final kinetic energy half mv square minus initial kinetic energy half mu square, that is the gain in kinetic energy, is equal to Q into voltage through which it is accelerated. Okay, from here we will get V square equal to U square plus 2 QV by M. Okay, where M is the mass and Q is the charge of the particle. Suppose the particle starts from rest, we can put U equal to 0. So the final velocity, or when a particle of mass M and charge Q is accelerated from rest through a potential difference V, then the final speed V will be root of 2 QV by M. See, small letter V represents final speed and capital letter V represents voltage through which it is accelerated. Now, if the intensity of electric field through which the particle is accelerated is uniform, See, this can be applied whether the field is uniform or non-uniform. Doesn't matter. But if the field is uniform, then this potential difference can be expressed as intensity of electric field into distance. Okay. Now, as a particle of mass m and charge q traverses a distance d along the direction of a uniform electric field E, means suppose there is electric field like this. Okay. Particle is released from here. Okay. And along the direction of the field, it moves through a distance d. Then what is the work done? Work done is E into d. Okay, that work done will appear as the kinetic energy. And the final energy, we can say E into d is the work done, and that is equal to increase in kinetic energy when it is accelerated from rest. So V will be 2 ED by m under root. Okay. 2 ED. See, this E is the intensity of electric field, into Q will give you the force. Okay, so Q into E, that is the force, into distance, that is the work done, that is equal to kinetic energy as it is accelerated from rest. So here the final speed will be 2QED divided by m under root. Okay, now see, let's consider the next case. Here we have a uniform electric field. There is a positively charged plate here and a negatively charged plate here. Now a particle of mass m and charge q is fired, is projected along the direction of the electric field. See, electric field is along the positive x-axis. See, I have shown the positive x direction and positive y direction. Now the particle is projected along the positive direction of x-axis, and the electric field intensity is also directed along the same positive direction of x-axis. So the particle experiences a force QE. Okay, accelerating force. Now see, the acceleration will be force divided by mass, and the acceleration equal to force is QE divided by mass is small m. Okay, now see, the initial velocity and the acceleration are along the same direction, and that is along the positive direction of x-axis. The intensity of electric field is also along the same direction. So the distance travelled, S equal to ut plus half a t square, we can use. As the displacement is along the x direction, let us represent the displacement by x itself. So see, x equals ut plus half. What is acceleration? Acceleration will be QE, okay, QE by m, okay, into t square. Okay, if the initial velocity is 0, okay, so x will be half QE by m into t square. Okay, now this is the displacement of the particle along the direction of the intensity of electric field in time t. Now see, this is a different case. Here we have uniform electric field intensity perpendicular to the initial velocity. See, a particle of mass m and charge q is projected along the positive x direction, and the intensity of electric field is uniform and it is directed along the positive y direction. Okay, see, motion along two perpendicular directions are physically independent. So here we can consider the motion along the x-axis and motion along the y-axis independently. See, along the x direction, there is no force acting on it. So there is no acceleration. So the horizontal component or the initial velocity u along the x direction will remain constant throughout the motion. So along the x direction, motion is with a constant velocity and the displacement will be simply velocity into time. See, initial velocity is only along the x direction. There is no initial velocity along the y direction, but there is an acceleration along the y direction due to the electric field. What is the force on the particle due to electric field? That is again Q into E along the y direction. See, Q into E along the y direction. Okay, that is the force. Initially, there is no velocity along the y direction. So when we consider the motion along the y direction, initial velocity u0, ut0, then displacement y will be half at square. This is the force. Divided by mass will give you the acceleration. Okay, so y, displacement y will be half. See, this is the acceleration QE by m. half a t square. This is the displacement along the x direction in time t, and this is the displacement along the y direction in the same interval t. Okay, so we have x and y expressed in terms of a third variable t. X is in terms of t and y is also in terms of t. Such equations are called parametric equations. So if we can eliminate the third variable, that is t, from x and y, we will get the equation for the path followed by the particle. Okay, now let's see from the first equation we will get t equal to x by u. That value of t we can substitute in the second equation. So we will get u equal to half qe by m, then for t square we can write x by u whole square. So we have got an equation in which the maximum power of y is 1. There is no y square term, there is no y cube term. And the maximum power of x is 2. Here we have x square term. See, in an equation, if the maximum power of either x or y is 2 and the maximum power of the other variable is 1, means in this case we have maximum power of x is 2 and maximum power of y is 1, then no doubt, unconditionally, that equation will represent a parabola. Let me repeat. If you have either the maximum power of x or the maximum power of y as 2 and the maximum power of the other variable as 1, definitely it will represent a parabola. So this is the equation of a parabola, or when a particle is projected into a transverse electric field. What do you mean by transverse electric field? Perpendicular electric field. Then that particle will follow a parabolic path. Children, in general, I can give you one more thing. See, whenever a particle experiences a constant acceleration along any direction other than its initial velocity, whenever a particle experiences a constant acceleration along any direction other than its initial velocity, path followed will be a parabola. Here, see, initial velocity is along this direction. Body has a constant acceleration, but it is not along the same direction. It is in a different direction. Here it is perpendicular. Need not be perpendicular always. If it has a constant acceleration along any direction other than the initial velocity, definitely it will follow a parabolic path. Now, see conductors. See, when a conductor is being charged by induction, then see the induced charge Q dash will be negative of the inducing charge, okay, in any conductor. Okay, and see the dielectric constant of a conductor in electrostatics means when there is no current through a conductor, its dielectric constant is infinite. Okay, now the intensity of electric field inside a conductor is 0. It's called electrostatic shielding. And intensity of electric field outside the conductor, that is sigma by epsilon 0, where sigma is the surface charge density. See, how do we get this? Consider a sphere. A sphere. What is the intensity of electric field on its surface? Intensity of electric field on its surface will be Q by 4 pi epsilon 0 r square. Q by 4 pi epsilon 0 r square. Okay, now that Q is the charge on the sphere. That charge, I can write that charge as the surface charge density into area, surface area. See, surface area will be 4 pi r square, okay, and surface charge density is sigma. Okay, so this is the intensity of electric field just outside the conductor, and see we have 4 pi r square in the numerator and also in the denominator. So finally what do we get? The intensity of electric field just outside a conductor will be sigma by epsilon 0. Okay, now see the electric force per unit area on the surface of a conductor due to its own charge is called mechanical pressure. Force per unit area on the surface of a conductor due to its own charge is called mechanical pressure, and it is sigma square by 2 epsilon 0. Okay, and see the surface of a conductor is an equipotential surface. Everywhere on the surface of a conductor, electric potential will be the same. It will be constant, irrespective of the size and shape of the conductor. Okay, so V equal to constant over the surface. And potential we can write, see, potential on the surface of a conductor is sigma r by epsilon 0. Sigma r by epsilon 0. See, what is the electric potential on the surface of a conductor? Electric potential on the surface of a conductor is see, Q divided by 4 pi epsilon 0 r. Q by 4 pi epsilon 0 r. That Q I can express as surface charge density into surface area. Surface area is 4 pi r square and surface charge density is sigma. So this is the potential on the surface of a conductor. So V. Okay, here we have 4 pi, here we have 4 pi, and here we have 1 r, and this r can also be cancelled. So what do we get? Sigma r by epsilon 0. So everywhere on the surface of a conductor, potential sigma r by epsilon 0 is constant. Okay, so V is constant, epsilon 0 is constant, so sigma r is constant. So on the surface of a conductor, product of surface charge density and radius is constant. When we take a perfect sphere, then the radius is constant everywhere. So the surface charge density also will be constant. But suppose we have an irregular body. Say like this, irregular body like this. Now children, see, here the radius is small. So the surface charge density will be more. But see, here the radius is more. So the surface charge density will be less, because sigma r is constant everywhere on the surface of a conductor. Okay, now see, what happens if a conductor is connected to earth by a conducting wire? See, the only thing that we can say that the potential of that conductor will be 0. See, we cannot say anything about the charge on it. Charge on the conductor will get modified such that the potential on it will be 0. Potential on a conductor connected to the earth will be 0 unconditionally. Okay. Now capacitors. See, when a charge capital Q is given to a conducting sphere of radius r, then the potential on its surface is given by V equals capital Q divided by 4 pi epsilon 0 r. The ratio of the charge given to a conductor to the potential to which it is raised is called its capacitance. Okay, so the capacitance of an isolated conducting sphere will be C equals Q by V, that is equal to 4 pi epsilon 0 r. See, in which 4 pi epsilon 0 is a constant, so we can say that the capacitance of an isolated sphere is directly proportional to its radius. See, what does this capacitance actually mean? It is the charge storing capacity of a conductor. If the capacitance is more, that conductor or that system is capable of storing more charge. Here the capacitance of an isolated sphere is directly proportional to radius, means a bigger sphere is capable of storing more charge compared to a smaller sphere. Okay, now see what restricts the charge that can be given to a conductor. Let us see. See, here we have a sphere of radius capital R mounted on insulating stands. Okay, that sphere is given a charge capital Q. Okay, that charge resides on its surface. See, as soon as this sphere is connected to the ground by means of a conducting wire, the entire charge on that sphere will move to the ground. But when there is no conducting wire between the sphere and the ground, charge will reside only on its surface and charge remains on its surface. Charge will not move to the ground. Why? because the medium that is in between the sphere and the earth, that is air, dry and dust-free air at 1 atmospheric pressure, is found to be a bad conductor of electricity, or it is an insulator, or it is a dielectric. What? Air. See, when there is a conducting wire between the sphere and the ground, the whole charge will move to the ground. But when there is air, that being a dielectric, the charge cannot move to the ground because it is an insulator. What? Air. Now see, the intensity of electric field on the surface of that sphere of radius capital R carrying a charge capital Q. Intensity of electric field on the surface of that sphere, that is kq by r square, and that k stands for 1 by 4 pi epsilon 0. Now see, the air surrounding that sphere is subjected to this much intensity of electric fields, or the electric field intensity on the surface of that sphere will be acting in the air surrounding it, and air is an insulator or dielectric. See, there is a maximum intensity of electric field that can be applied to a dielectric without losing its dielectric property, and it is called the dielectric strength of the dielectric, or dielectric strength of the medium. For air, it is 3 into 10 raised to 6 volt meter raised minus 1. What does it mean? As long as the intensity of electric field acting in air is less than this value, it will remain as dielectric. But whenever the intensity of electric field acting in air exceeds this value, it will start conducting. Now see, children, this is the intensity of electric field on the surface of that sphere. When charge given to the sphere is increased, the intensity of electric field on its surface will increase. The electric field acting in the surrounding air will increase. So we can increase the charge on the sphere until the intensity of electric field on its surface becomes equal to 3 into 10 raised to 6. Because the surrounding air is subjected to that much intensity of electric field. See, if the field on the surface of that sphere exceeds this value, the whole charge on that sphere will go to the earth. So we cannot give unlimited charge to any sphere or any conductor. We can give charge until the intensity of electric field on the surface of the conductor reaches the dielectric strength of air. Okay, so the intensity of electric field on the surface of this conductor, that is limited. Okay, see, this can be 3 into 10 raised to 6. That's a fixed value, and this k is also fixed. So we can say q by r square is constant. So q is proportional to r square. When the radius of a sphere is more, then more charge will be required to reach the intensity of electric field on its surface, this value 3 into 10 raised to 6. For a smaller sphere, a relatively smaller charge can make the field intensity on its surface 3 into 10 raised to 6. So when the radius is more charge will be required to reach this value maximum. Okay, so we can say that a bigger sphere will be capable of storing more charge, or its capacitance will be more compared to a smaller sphere. Okay, now this is an isolated sphere, but in a regular spherical capacitor there will be two concentric spheres. See, the inner sphere is given some charge, say plus q, and the outer sphere will be connected to the ground. See, whenever a conductor is connected to the ground, see, we can only surely say that the electric potential on that conductor which is connected to the ground will be 0. Potential will be 0 if it is connected to the ground. We cannot predict the charge on that conductor. Charge need not be 0. Charge will be adjusted so as to make its potential 0. Okay, now see, this is the capacitance of a regular spherical capacitor which is having two concentric spheres of radius A and B. So the capacitance will be 4 pi epsilon 0 AB by B minus A. And this is a regular cylindrical capacitor. There will be two coaxial cylinders. Okay, inner cylinder is given some charge and the outer cylinder will be connected to the ground. Okay, so this is the capacitance 4 pi epsilon 0 L divided by log B by A, where B is the outer radius and A is the inner radius, L is the length of each cylinder. Now we have our wonderful parallel plate capacitor. Okay, there are two identical metal plates, each of area say capital A kept parallel to each other, at separation say small d. Okay, now see, one plate is given a charge plus q and the other plate is connected to the ground, as we have done in spherical capacitor and cylindrical capacitor. See, the intensity of electric field exists only in between the plates and it is sigma by epsilon 0. So the potential difference between the two plates will be E into D, where E is the intensity of electric field and it is uniform. Okay, so yeah, potential difference V equals E into D, and intensity of electric field E equals Q by A. Q by A stands for sigma, that is the surface charge density. So we will get V equal to this thing, and the capacitance is charge divided by voltage or potential difference, and that is equal to epsilon 0 A by D when there is air in between the plates. Now suppose the medium between the plates is being filled with a medium of dielectric constant K, then the capacitance C dash will be K times the capacitance with the air in between the dielectrics, in between the plates. Okay, now see, let's see the next part, what we have. See, now the space between the plates is partially filled with a slab of thickness T and dielectric constant K. Okay, now see, the intensity of electric field in air is E0 and the intensity of electric field in dielectric will be E0 by K, where K is the dielectric constant. Okay, now we will have the expression for the capacitance, that is epsilon 0 A divided by D minus T plus T by K, where T is the thickness of the slab and D is the separation between the plates. Now suppose the space between the plates is being filled with dielectric. What does it mean? The thickness of the slab will be equal to separation between the plates. Means T equal to D. When you put T equal to D, this will become D minus D, means it will vanish that term. Okay, and here we will have D by K, that K will go to the numerator, so it is epsilon 0 Ka divided by D. Okay, see, the same expression we have got earlier, no? Okay, next this is grouping of capacitors. This is also wonderful. We have three capacitors, say C1, C2, C3, connected in series across a source of voltage capital V. And see, as these capacitors are connected in series, the charge in all the three capacitors will be the same. And voltage across a capacitor is given by V equal to Q by C. As the charge on all the three capacitors are the same, see, Q is same, so we can say this equal to, and Q is constant, it does not change as we move from one capacitor to another when they are connected in series. So let us say V proportional to 1 by C, voltage across each capacitor will be inversely proportional to their capacitance. Okay, so V1, V2, V3, the voltage or potential differences across the three capacitors will be in the ratio of 1 by C1 is to 1 by C2 is to 1 by C3. Suppose for example, suppose we have connected a 220 volt supply across three capacitors, say 100 microfarad, 200 microfarad and 300 microfarad. Okay, say 100 microfarad, 200 microfarad and say 300 microfarad, 300 microfarad. So the ratio of the capacitances will be See, it will be 1 by 1 is to 1 by 2 is to 1 by 3. Okay. See, to make this a simple ratio, you have to multiply throughout by LCM. That is 6 here. So it will be 6 is to 3 is to 2. So the total voltage I have told you, 220 volt in this example, 220 volt, say it is 220 volt. Then that 220 volt is to be divided in the ratio 6 is to 3 is to 2. How do you divide? You have to divide the total voltage into 6 plus 3, 9 plus 2, 11 equal parts. When this 220 divided by 11, each part will be 20 volt. See, 20 volt, 20 volt, 20 volt, such 11 equal parts, in which the voltage across the first capacitor will be 6 parts, means 6 into 20. Means voltage across the first capacitor will be 20 into 6. Voltage across the second capacitor will be 20 into 3 parts, and voltage across the third capacitor will be 20 into 2 parts. Okay. Now children, this will be 20 into 6 means that is 120 volt across the first capacitor, that is 100 microfarads. And 20 into 3, that is 60 volt across the second capacitor, which is 200 microfarad. And finally, the voltage will be 40 volt across the third capacitor, that is 300 microfarads. So when the capacitance is more, the voltage across will be less if these are connected in series. Okay, now see, let us see the expression for the equivalent capacitance when a number of capacitors are connected in series. That is given by 1 by C equal to 1 by C1 plus 1 by C2 plus 1 by C3. See, in series combination, the effective capacitance will be smaller than the smallest. See, in this example here we have 100 microfarad, 200 microfarad, 300 microfarad connected in series. Then the effective capacitance of all the three must be smaller than the smallest among the individual. Means that it should be smaller than the 100. If you get see an equivalent capacitance which is more than 100, definitely it is wrong. Okay, you should get an effective capacitance that is smaller than the smallest among the individual capacitors. Okay, now suppose we have n identical capacitors. N identical capacitors connected in series. So the effective capacitance will be C by N. Okay, now let us see the next, see what we have. We have 3 capacitors connected in parallel. When a number of capacitors are connected in parallel, the voltage across each capacitor will be the same. See, the charge on each capacitor Q equal to CV, in which see voltage across all the capacitors are the same. So the charge will be directly proportional to capacitance. Suppose here we have connected say 100 volt, okay, and here we have say this is 1 microfarad, okay, and suppose this is 2 microfarad and this is 3 microfarad. The voltage applied is 100 volt. So the voltage across this will be 100 volt and charge on it will be 1 into 100, means 100 microcoulombs. The voltage across this second capacitor also will be 100 volt. Charge will be 200 microcoulomb. Okay, capacitance 3 microfarad, voltage across that capacitor also will be 100 volt. Whatever voltage is connected, that will appear across all the 3 capacitors. Okay, and charge drawn by each capacitor will be proportional to their capacitance. See, capacitance I have told you, it is the charge storing capacity. So, if the capacitance is more, it will be capable of storing more charge and it will draw more charge from the given source. Okay, now here the effective capacitance is sum of the individual capacitances. So it will be greater than the highest value. Okay, here we have 1 microfarad, 2 microfarad and 3 microfarad. Effective capacitance will be more than 3. Right? Okay, now suppose an identical capacitors each equal to C are connected in parallel. The effective capacitance will be NC. Okay, Now see, let's see what is next here, energy stored in a capacitor. In electric circuit we have three elements: resistors, capacitors and inductors, in which resistors are called passive elements, means they dissipate energy. Capacitors and inductors are called active elements, they do not dissipate energy. See, all the three elements are used, capacitors, inductors and resistors are used to control electric currents. Resistance can be used to control AC as well as DC, but at the expense of some energy dissipation. Capacitors and inductors can also be used to control the current without any loss of energy, but what is the limitation? Inductors and capacitors cannot be used to control unidirectional current. Inductors and capacitors can be used to control only alternating current, but there is no loss of energy. And the disadvantage is it cannot be used in DC. Resistors can be used anywhere in DC as well as in AC, but current can be controlled at the expense of some energy. Okay. Now children, anyway, see, capacitors store energy in electric fields. Inductors store energy in magnetic fields. See, what is the energy stored in a capacitor? That is represented by capital U, and it is equal to half CV square, where C is the capacitance and V is the voltage between its plates. It can also be written as QV by 2 or half Q square by C. Now see, a energy density means that is the energy per unit volume. See, this is an important expression that is represented by small u, and it is equal to half epsilon 0 capital E square, where E is the intensity of electric field and epsilon 0 is the permittivity of free space. Now see, we have a capacitance capital C connected across a source of voltage capital V. This complete voltage will appear across the capacitor. Then see, some charge Q will be stored in the capacitor. See, what is actually happening there? See, both the plates of the capacitor were electrically neutral. So this cell takes plus Q charge from the plate on the right side, and that charge will be transferred to the plate on the left side. See, the potential difference between the terminals of the cell is capital V. What does it mean? In order to take 1 coulomb of charge across the terminal, V work is to be done. But here the cell has taken capital Q charge from this plate across the terminals. To take 1 coulomb across the terminals, V work is to be done. But here Q coulombs are taken across the terminals. So QV work must be done by the cell. Okay. See, work done by the cell, W equal to QV. When the capacitor is given a charge Q, and if V is the voltage across its terminals, the energy stored in the capacitor will be half QV. See, work done by the cell in that process is QV. So whatever work is done by the cell, only half of it will be stored in the capacitor as its energy. So while charging a capacitor, a cell is only 50% efficient. What is the efficiency? It is only 50%. Okay. Now see, effect of dielectric. See, here we have a capacitance parallel plate air capacitor, and its capacitance is C0. It is connected across a source of voltage V0. Then the voltage across the capacitance will become V0, and the charge on the capacitor is Q0 equal to C0 V0 with the air in between the plates. Okay, the energy stored in the capacitor will be half C0 V0 square, and the intensity of electric field between the plates of the capacitor, that is equal to V0 divided by D. Now see, keeping the cell connected to the capacitor, suppose the space between the plates is filled with a dielectric slab. The dielectric constant, say it is K. Now see, the voltage as the cell is kept connected to the capacitor, the voltage across the capacitor will remain constant. Okay, so V remains same, and as the space is filled with the dielectric, the capacitance will become epsilon 0 Ka by D, or it is KC0, where C0 is the capacitance with the air in between the plates. So the capacitance is definitely increased. Now the charge storing capacity is increased, and the cell is still remain connected to the capacitance. So the capacitor will draw more charge from the cell. Okay, so the charge drawn by the capacitor, okay, that is equal to CV, the new capacitance and the new voltage. See, the voltage across the capacitance is same as before, but the capacitance is increased K times. So it will be C can be replaced by KC0. So we will get KC0 V0, in which C0 V0 is the charge initially stored in the capacitor. So this is equal to KQ0. So the charge stored in the capacitor also increased by a factor K. Okay. Now let's see the energy stored in the capacitor. Let's use this formula, half CV square. Half this C can be replaced by KC0. So it will be half KC0 V0 square or KU0. So energy stored in the capacitor also increased K times. Okay. Now intensity of electric field. See, voltage across the capacitor remains same. Separation between the plates also remains same. Okay, so the intensity of electric field E will be V0 by D. E will be V0 by D, and let us say it is same as E0. Okay, this one, okay, this one is same as E0. Okay, the intensity of electric field between the plates of the capacitor remains same as before. Okay. Now let's try the next case, means the capacitor as before, it is again the parallel plate air capacitor C0, capacitance is epsilon 0 A over D, that is connected across a source of voltage V0. So the voltage across the capacitance will become V0, and the charge on the capacitor will be C0 V0. Okay. Now see, energy and intensity of electric field between the plates are also given. Now the capacitor is disconnected from the cell. Okay, the capacitor is here. Here the capacitor is disconnected from the cell. Its terminals are floating. Its terminals are not connected anywhere. So there is no path for charge transfer. Okay, so whatever charge is stored in the capacitor, it will remain as constant. Okay. Now the capacitance C equals epsilon 0 Ka by D, that is KC0. So the capacitance is increased. Okay. Now voltage V equal to Q by C. Q remains same. Okay, but the denominator capacitance is increased. So C can be replaced by KC0, in which Q0 by C0, see here, Q0 by C0 can be written as V0. So we will get V0 by K. Means the potential difference between the plates of the capacitor is reduced by a factor K. Okay. Now energy stored in the capacitor is Q square over 2C. The Q remains same as before, that is Q0 itself. But the capacitance earlier it was C0, now it is KC0. Okay, so the energy stored in the capacitor will be U0 by K, or again reduced by a factor of K. Okay, now finally we have the intensity of electric field E, that is equal to V by D. V is now V0 by K, whole divided by D, we can write V0 divided by KD, in which V0 by D can be replaced by E0. So the final intensity of electric field is E0 by K. It is also reduced by a factor K. Okay. So children, please understand that. See, if the cell is kept connected to the capacitor, then the voltage will remain same. And if the slab, a dielectric slab, is inserted between the plates after disconnecting from the cell, Then see, the terminals of the capacitor will be floating, means the terminals are not connected anywhere. So whatever charge is stored in the capacitor, that will remain constant. Okay, now let us consider another case in which see, a number of charged liquid drops combine to form a big drop. Okay, suppose small q is the charge carried by each droplet of radius small r, and when small n identical such droplets combine to form a big drop of radius capital R, volume of liquid will remain constant, will remain conserved. Okay, so this is the volume of n droplets, means the volume of each droplet into number of droplets, and this is the volume of liquid in the resulting drop. This must be conserved. So we will get the radius of the resulting drop as n raised to 1 by 3 into small r. See, the capacitance of an isolated sphere is 4 pi epsilon 0 r. So capacitance is directly proportional to radius. So when the radius becomes n raised to 1 by 3 times, then the capacitance also will become n raised to 1 by 3 times. Okay, n raised to 1 by 3 times, yeah, C equals n raised to 1 by 3 times C0, where C0 is the capacitance of each small droplet. Now suppose V0 is the potential, electric potential on the surface of each small droplet, then the electric potential on the surface of the resulting big drop will be capital V equal to n raised to 2 by 3 times V0, and the energy stored in each droplet is U0, and the energy stored in the resulting drop will be n raised to 5 by 3 times U0. Okay, now see, yeah, okay, next thing we will see. Now children, we have another wonderful concept here. See, we have a capacitor C1 that is connected across a source of voltage V1. So it will get charged to a voltage V1, and another capacitor C2 that is connected to another source of voltage V2. Okay, now both the capacitors are disconnected from the cells, and suppose the two capacitors are connected together in parallel with their positive to positive and negative to negative. Okay, this will see, positive plate of the first capacitor connected to the positive plate of the second, and a negative plate of one connected to the negative plate of the other. Okay, so these two capacitors will attain a common voltage that is given by V equal to C1 V1 plus C2 V2 over V over C1 plus C2. See, so there will be some energy loss definitely, and that energy loss is given by half C1 C2 by C1 plus C2 into V1 minus V2 whole square. A similar wonderful example that we have done in mechanics. A particle of mass m moves with a velocity u1. It makes or it collides with another particle of mass m2 moving with velocity u2. After collision, they stick together and move with a common velocity that is given by exactly similar formula, V equal to m1 u1 plus m2 u2 divided by m1 plus m2. See, in that situation there was some loss of kinetic energy, and the loss of kinetic energy is given by the beautiful expression half m1 m2 by m1 plus m2 into u1 minus u2 whole square. What is u1? It's the initial velocity or velocity of the first body before collision. And what is u2? It's the velocity of the second body before collision. Okay, now okay, see, same thing, similar form. Here also the energy lost will be half C1 C2 over C1 plus C2 into V1 minus V2 whole square. Okay, now see, suppose the second capacitor is initially uncharged. What does it mean? Second capacitor initially uncharged means see, this V2 will be 0. V2 will be 0. Then initially the whole energy was stored in the first capacitor. Then what fraction of the energy stored in the first capacitor is lost? See, this much is the energy loss, and that energy loss will be equal to delta U, that is a half. Okay, then C1 C2 over C1 plus C2 into V1 square. Okay, this much is the energy loss. Okay, divided by initial energy stored in the first capacitor. Okay, that will be see delta U divided by initial energy U. Okay, this is equal to C2 divided by C1 plus C2. How do we get that? Because this U is half C1 V1 square. So when we divide this one by half C1 V1 square, we will get C2 divided by C1 plus C2. See, another wonderful idea is, suppose these two capacitors are connected with the reversed polarity. Means, see, positive plate of one capacitor is connected to the negative of the other. See here, see, we have a positive plate of the upper capacitor on the left side, negative plate of the lower capacitor on the left side. So positive plate of one capacitor connected to the negative. Okay, negative plate is connected to the positive of the other. Okay, like this they are connected reversed. Okay, see, in mechanics, if the two bodies were moving in opposite direction, see, the common velocity will be m1 u1 minus m2 u2 by m1 plus m2. Similarly here, the see, potential differences are in opposite direction. Okay, so we will get V, common potential C1 V1 minus C2 V2 divided by C1 plus C2, and again there will be energy loss, great loss. The energy loss will be high in this case, because instead of V1 minus V2, here it is V1 plus V2. Okay, so this is the expression for the energy loss. Okay, now children, before I conclude, let me tell you one more thing. That is, suppose a capacitor C is connected to a source of voltage V, and suppose the plates of the capacitor are separated by means of insulating handles. Okay, after disconnecting from the cell. Means the capacitor is charged, it is disconnected from the cell, and after that the plates are separated by means of insulating handles, or the separation between the plates is increased. See, once it is disconnected from the cell and its terminals are floating, or when its terminals are not connected anywhere, whatever charge is stored in the capacitor, that will remain constant. But when the separation is increased, what happens? Capacitance will get reduced. Capacitance will decrease. Now, potential difference between the plates of the capacitor, that is V equal to, see, V equal to C Q divided by C. When the when the separation between the plates is increased, capacitance will decrease, because see, this capacity V equal to Q by C, and we have capacitance C equal to epsilon 0 A divided by D. That D I have increased by insulating handles, means charge cannot escape. So capacitance will decrease and the potential will increase. Capacitance will decrease. And what happens to the energy stored in the capacitor? See, energy stored in the capacitor formula is Q square over 2C. That Q remains constant and capacitance C is decreased. So the energy stored in the capacitor will increase. Okay. See, all these happen when a capacitor is charged and it is disconnected from the cell, and the separation between the plates is increased by means of insulating handles. Okay, see, suppose the separation is reduced, what will happen? The capacitance will increase. As said earlier, charge will remain constant, then the potential will decrease and energy will decrease. Okay, now suppose the capacitor is kept connected to the cell, then the voltage will remain constant. Now if the plates are further separated, then the capacitance will decrease. So charge stored in the capacitor will decrease. Energy stored in the capacitor will decrease, because the voltage remains same as it is kept connected to the cell. Okay, so children, I have explained all important things. Okay, from the basics to advanced. I hope you all enjoyed. Thank you for watching and best of luck.